MCR was designed following a client's request for a robot that was capable of picking up small items, such as Hot Wheels cars, and delivering them into a bin whose rim is about 30 centimeters from the floor. The robot had to be interactive, which means no autonomous robots could be used here, and it had to be self-propelled, and so there couldn't be any interaction between the user and the robot once it was set down. The robot also had to be able to drive for a minimum of 1 hour on a single charge. The basic design for MCR was inspired by EOD, or Explosive Ordnance Disposal robots. Those are the robots that are used by police and military to go out and inspect for explosives or if they need to manipulate or handle any hazardous materials. And if you're not familiar with them, they're robots that usually have like tank tread for movement, and they also have an articulated arm, usually with a claw, but sometimes other tools on the end of them. The robot was mostly 3D printed here with an artillery sidewinder 3D printer. The way we designed everything was modular, and so everything could be printed piecemeal, test for proper fit, and then it could all be printed at once. And what that allowed us to do was pump out a lot of prototypes for each component individually instead of having to print a whole chassis all at once, which takes several hours sometimes. So this was done for all the components. First the drive motors, and then the servos and the claw, and everything was made sequentially, but in small parts. And once everything fit the way we needed it to, prototype was printed at full scale, and that was presented to the client. And it did function, but the client did have some further requirements that they wanted to see implemented. So just for reference, this is an image of an EOD robot. So you can see it has the articulated claw arm right out front, and it's also got the tank tread. These usually have another degree of movement there in the center of the arm so that things can be manipulated a little bit more. Also, the claw can be rotated on this particular robot. Those were not design requirements set by the client, so those were not implemented. However, they could be. Here you can see the chassis design a little bit better. As it spins around, you can see how everything is laid out and the different components here. This is actually the second prototype that we've made for the client. The scoop was added, the chassis was stretched a little bit longer, but the overall design has stayed the same. The chassis for MCR was designed in Design Spark Mechanical, and again, it was printed in-house on an Artillery Sidewinder X1 3D printer. We chose to print it in PLA, especially for these prototypes, because we were rapidly pumping these out, and PLA can be printed very easily and very rapidly. Another perk is that PLA is rather inexpensive, and so when we were test fitting things and when things weren't fitting quite right, component-wise, we weren't losing out on a whole lot. The size was limited by the client request. Again, they wanted a robot that was rather small and could manipulate objects inside of a child's playroom. And so it needed to be rather small. Also, the track dimensions, that was a huge limiting factor. So the tracks that we used from wheel axle to wheel axle was only 85 millimeters. And so the whole chassis had to fit more or less within that confined space. We did stretch it a little beyond the tracks just for better maneuverability and so that we could increase the payload that it could lift. And as such, again, the component orientation within the chassis was dictated more by the size of the robot than anything else. Moving on to the drivetrain components for MCR, driving the tracks are 2 drive motors, so the tracks can move independently, and those are Pololu micro gear motors at a 1,000:1 gear ratio. Selecting that high of a gear ratio was to give it more maneuverability at the sacrifice of speed. So those motors are actually only turning at 35 RPM, and that's very, very slow. And so it doesn't have a very high top speed, but that allows the user to maneuver it very very precisely, which is needed, especially because that arm is not articulated. And so the only way to maneuver the arm into position is by using the drivetrain itself. Now, those motors do have a very high stall torque, though, given that high ratio. Now, the theoretical that you see on the screen is the stall torque given is a theoretical. You can't actually reach that stall torque with these motors. The gears on the inside of the motor will actually strip, and you won't actually ever reach that stall torque. The tracks that those motors are mounted to are also Pololu. Those are 30-tooth track sets, and as I was saying before, the axle-to-axle wheel distance is only 85 millimeters, and so that was a big design factor. The diameter of those wheels, and so we can calculate out how fast this thing moves, you have to take the wheel and track diameter. In this clip, you can see how the arm articulates down and the claw grips an object. This clip is also extremely useful to see how the arm manipulates around the object due to those pads inside the claw. This is another view of the lifting mechanism, and this one really illustrates how that claw wraps around the objects. Now that we've seen how the arm and claw work together, we can go into a little bit more detail about how those were created. So both of those were modeled in Design Spark Mechanical and edited in Blender. Both of them were printed on the Sidewinder X1, again in PLA, because we went through several iterations and just wanted to pump them out for prototyping. The servo for the claw itself was selected not because it has the highest stall torque, but because it has one of the highest torque to weight ratios. And that's important because the lifter arm can only lift a finite payload, and that servo being out at the end of that claw is actually kind of part of that payload calculation. And so the heavier that servo is, the smaller the payload that the arm is able to lift. Now, moving down to the servo for the lifter arm, that one, the weight was not an issue. And this one has a much, much higher stall torque, as you can see. This one, it was selected just purely for the stall torque rating and, of course, cost. Moving to the onboard electronics for MCR, we have both of the drive motors are powered by a dual H-bridge L298N. The onboard battery is a 2.2 amp hour, 11.1 volt LiPo. And that battery was chosen specifically for its capacity. Not just for capacity, of course, but the 2.2 amp hours allows it to reach that 1 hour drive time that the client required. The Turnigy 6-channel radio receiver, that we chose just for availability purposes. Now, you could use a 4-channel radio receiver in this robot. However, we did not have one on hand. The high-tech battery elimination circuit, that takes the 11.1 volts from the battery, and all that is a voltage regulator, and it steps that down from 11.1 volts to 6 volts, which is what's required by the radio receiver. The Arduino Pro Micro was chosen more for size than any other reason. The Pro Micro has a smaller memory capacity as compared to some of the larger variants of the Arduino. However, it's much, much smaller. The Pro Micro also has an onboard USB, which was important for manipulating the code once it was on the robot. Once the Pro Micro was soldered in place, it's very difficult to move it from inside the robot and then put a separate circuit on it. It was a nightmare trying to figure out the logistics of manipulating code once it was on the robot. So the Pro Micro is chosen because it's very small, but it still has that USB connection. Thank you all for watching. If you have any questions about anything that I've talked about, or if you want anything explained in more detail, you can always get a hold of me or leave a comment down below.